Okay, welcome back to the chapter 4. Then we finish our the first group of instruction set is the moving set and also the arithmetic set. In this one, we will talk about logic instruction set. For the logic instruction set, it means that you try to do some logic operations between two variables or between operands. In this case, the first one we have the command or mnemonic code is called AND and we follow by S and condition as usual. Then we have the explanation as RD equal to RN and with the operand 2. So what's gonna happen in the real situations? It means that bit number 0 of RN will go through the AND gate with the bit number 0 of operand 2, then the output will store in the bit 0 of RD and it will go on until we have the bit number 31 of Rn and with the bit number 31 of operand 2 and the output will store in the bit number 32 of RD. So this is the bit operations. For the next one, BICs. For the BIC is RD equal to Rn and with the not operand 2, it means you pass operand 2 with the not gate. First, you just change logic 1 to 0, 0 and 1, just only a not gate. Then you add with the Rn. For the next one, BIC with this one. For the BICs, RD equal to RD and with the not Rn. Okay. For the next one, ORR. In this one, it means that RD equal to Rn or with the operand 2. ORN. For the ORN is RD equal to you should change this one to RN or with the with not operand 2. Okay, let me change this. Okay, to N. Then we have EOR. For the EOR is exclusive or RD will equal to Rn exclusive or with the operand 2. The next one is NEG. For the NEG is RD equal to not Rn. And the next one ASR. This one they say is arithmetic shift right. So what is it? Before you understand arithmetic shift, you have to know understand the shift operation first. Then we move to LSL first. For the LSL is a logic shift operation to the left. Then if you have LSL with RD, Rn, operand 2, so what gonna happen? The explanations should be RD equal to Rn and you shift Rn by operand 2. Okay, this one is called logic shift left. For the logic shift left, this is examples. If you have Rn of 50s, then you have to do some logic shift by 1. I just make operand 2 is equal to 1. In order to understand it, you have to change RD from decimal number to binary numbers. You will find out 50 is 0011 0010 and you perform shift it by 1. It means that you shift all the informations to the right by 1 bit. Then RD will become 0 1 1 0 0 1 0 0 and if you change it back to decimal numbers, you will find out this is 100. This is called logic shift left. Okay, how about logic shift right? Logic shift right do the same thing but different directions. In this one, you shift to the left and then you shift to the right by this one. So RD equal to Rn and do shift right to by the numbers of it that represented by the operand 2. How about arithmetic shift left or arithmetic shift right? So in this case, sometimes we have the negative number, right? For the negative number is actually it's not the real numbers in the fixed point environment or digital because digital don't have any negative numbers. We just use most significant bit as the sign bit that show this is negative or positive. Therefore, this bit should not be altered, right? Because this is arithmetic. Arithmetic means that we have the positive and negative. Therefore, they will try to shift anything else rather than this one and try to keep the informations of the negative numbers after we do some chip operations. For the next slide, we will find the examples. For the next one, the next command is called ROR. For the ROR is rotate operand by operand two times. It means that for your Rn you have to rotate. So what is the chip and rotate? For the chip you just chip it and that's it. Everything else is gone. But for rotate it means that when you chip anything out of the bit, have to going back to the front of it. If you chip to the left and if you chip to the right, they will go back to the end of your group of the numbers. Okay, that's it. And the last one is RRX. This one is we will put carry flag into our operations is also. Okay, this is examples of the arithmetic and also a logic chip rep or chip right. Okay, this is right arithmetic chip. First of all, when you take a look here, you will find out that this is a negative numbers because MSB is equal to 1. Then if you would like to perform the arithmetic shift, for what's gonna happen? If you shift by ones, it means that right now you shift to the right hand side, then the 1 here become here, 0 here, 0 here, 1 here, 0 here, 1, 1, and the last one is gone because you shift it, you don't keep it. And MSB here is show 1, then it will become 1 in here because we try to keep the sign of the numbers in this case. Okay, how about a left arithmetic shift? In this one is also, if you can see, it shift to the left, right? But in this one, you have to make sure that the last one here is still 0. Okay. For this one, you will find out very complex situations. Why? Because if you have 1 here and you shift this is 0 into here, so what is gonna happen? Your sign is gone, and this is not good. Therefore, if you go back a little bit, you will find out why we have just only ASR in this fashion, because we can be sure that we can keep the sign if we do just auto arithmetic shift right, but we cannot keep the sign if we do arithmetic shift left. Okay, and this one will not happen in our situations. Then we don't have any command to use this kind of structures or this kind of left shift for arithmetic. But for logic is fine because we don't care anything about this one. The next one is rotate. For the rotations, as you can see, rotate means you have one here, they shift to the next one, and so on. And the last one will going back to the first one if we do some rotate right. For the rotate left, we do opposite directions, and the most significant bit become least significant bit, like this one. Okay, then but one thing I would like to make sure that for this one, be careful. Our registers in our CPU is 32-bit. When you do the arithmetic chip or rotate or logic chip, you have to write down all of the bits that happens. Otherwise, you can create some problems for the calculations or the chip or the rotations. Okay, this is, I would like to make sure that you understand our register is 32-bit. Okay, then we go through this example again. For this one, for the S and con, you already know, and operand, you already know that how can we find the value and what's gonna happen if you paste S and also the suffix condition into our commands. Then this is the first examples, ORN. For the ORNs, R0, R0, and R0. It means that R0 equal to R0 or with the not R0. Okay, and this one we don't put S in here. It means that this operation will not affect ASPR register at all. The next one, BIC equals, so we have to check it's equal or not first. If it's equal, then we do operation BIC for R3, R3, and 1. And this one is R3 equal to R3 and with the not 1 and 1. You can see here that why I say everything is 32-bit, because if you not this one, it will become 1 and this is not, and this one is not 32, this one is hexadecimal numbers. Therefore this is 32-bit, and you can see here is very changed when you pass through. Not you have F and E, okay, and this one, but because of we don't put S in here, so this action will not affect ASPR at all. The next one EORS, and this one you will see you have S here. It means that your action will affect ASPR registers. Then the output should be R3 equal to R4 executive OR with these numbers. Okay, but you have to write down in bit forms, binary form. Then you can do executive OR bit by bit with the value inside your registers are 4. Okay, and this one they would like to explain more about this one. Okay, if we have binary number 117 in the decimal number or 011100101 in binary numbers, and if we perform arithmetic shift right by 1 bit, we got the binary of 00111010 is 58 decimals. Okay, if we do the binary numbers of 1010 is -6 decimal, then we perform arithmetic right shift by 1. We got the numbers of 1101 is -3 decimal. Okay, this is examples that we already talking about. How can we do some shift operations for the arithmetic operations to keep the sign of it. Okay. Next one is compare instructions. Okay, before this, somebody will ask, how can we so sure that if we put the condition suffix at the tail of the command, it will operate that command, and how can we get that suffix? How can we get the conditions that display on suffix conditions? This is a command that create the conditions for our suffix conditions. The first one is called CMP. For the CMP, we try to compare RD with the operations, and it will update the flag in ASPR definitely. As you can see here, we don't have S because it's automatically have S inside this command. It means that if you compare is equal, then it will show equal. And when you compare is greater than, then they will show greater than. If you compare and you will find out is less than, they will show less than. And this one is straightforward because you just do operations RD minus operand 2. The next one is a little bit complex because your command is not CMP anymore, becomes CMN. For CMN, it means that you try to compare with the negative number of operation 2. Then if your operation 2 is negative, then negative with negative become positive or plus sign here. Then they will compare RD with the negative numbers of operation 2 or RD plus R2. Then what the output that happens will alter the bit in ASPR. Okay, if this one is a little bit confused for you, you can think of CMN is compared with negative number of operation 2, and that's it. They can follow of the same result of this operation. For the next one, TST. For the TST, you try to find the results of RD and with operand tools, then update the flag in ASPR. Okay, this one you do an operation. It's useful sometimes. For this one you try to compare the numbers, but this one you try to add with the bit inside RD and operand 2. The next one of TEQs. For the TEQs is you try to find the result of RD executive or with operand 2 and update the flag in ASPR. Okay, and this is examples. For the examples, we do something like this: CMP R4 R1. You try to compare R4 with R1, and the result will store in ASPR, right? Because it's alter the bit, the flag bit inside ASPR, which is a negative bit, 0 bit, carry bit, and also overflow bit. How about the next one, AST EQs? Okay, first of all, you find out these conditions, right? So you have EQs is equal, you have to do this operation when is equivalent or equals. If it's equal, what you gonna do? You try to do R1 executive OR with 12, and 12 is 0x 000 and the output of this one will affect the fact in APSR. For the next group of memory of the instruction is called memory access instructions. Okay, because our memory access can be unaliased, right? For the STM32 Cortex-M3s, therefore the size of the data can be 8-bit, 16-bit, 32-bit, and also 64-bit. But for the 64-bit is almost not happens in our situations, because most of the time we know that our system is 32-bit. Therefore, sometimes we don't want to do anything greater than 32 bits. Okay, this is summarize how can we do some memory access instruction. But basically, in this one, we just have only two commands for memory access. It's called LDR. It means load. For the load, it means that you copy the value inside the specific locations of your memories and copy and save it into some registers. The next one is called ATR or store. For the store, it means that when you have some value inside your registers, you would like to keep that value stored inside the specific locations of your memories that you use STR. And we do something called suffix by the size of the data, as I show in here. If you find out there are LDRHH in here, for HH it means size half word. It means that you would like to store just only 16 bits into your specific location in the memories. And this is load. You just would like to load just only 16 bits inside your memory and store into your registers. And this one, we try to write something back to the memory using STR. And STR here you will find out that this should be HH. It should be HH. Okay, for this one, for the HH, it means that you try to copy from register and store it back to memory, but just only 16-bit. You don't want to go up to 32-bit. If you have LDR and STR normal form right here, you just deal with 32 bits. When you would like to copy the value from memories, or you would like to store the value or data into your memories. And if you want to go unsigned half bit, you just put H here and H here, no S is fine. How about 8-bit? For the 8-bit, you have two options, is SB or just only B. For SB, it means you have the signed bit. For the B is unsigned bit. And somebody will ask, and why we have to do this? Why we need a signed bit or unsigned bit? It depends on your code. Because sometimes, if you deal with non-signed variables or non-signed value, then you can go read from non-signed. But if sometimes you would like to save a sign, then you can keep the sign into this one. Okay, let you think about this one. If we have a lot of bits that installed inside your memories, and if you would like to read half word sign, it means that they will take a look the most significant bit, right? The most significant bit of 16-bit will show the size of your data, right? And that specific most significant bit of 16 bit will be displayed as output when you store inside your registers. Let me explain like this. Okay, this is your memories or your register, and you will find out this is 1. Okay, this is 16 bit. And you would like to keep this one to your, this is memory, and you would like to keep into R0 in this one. Then because of this one, if you keep just to the R0, but R0 is 32 bits, therefore if you did not use SI half word to load from your memory to store inside R0, R0 will place the most significant bit of R0 and equal to 0. It means that your sign that store inside your memory is gone. Right now from negative numbers become the positive numbers. And if you load, just use this one to have to specific that is a sign, then they will change these values and make one appears at the most significant bit of R0 for you. It means that you keep the negative sign of your data. That is the reason why we have the separate command to load a signed and unsigned bit from your memory and store signed and unsigned bit into your memories. Okay, and this is what we try to do. As you can see, there's a lot of things that happen here, and basically you can go through these informations because I already told you that in order to access your memories, you have 3 kinds of things that you can do, right? It's let me go back a little bit because sometimes you don't remember this one. Okay. Here, because we have 3 addressing mode. For the first addressing mode is offset. If they follow like this, is just combine this one and point into the locations of the memory and copy it and store into your memories, or save from your R into the memories by using this one. The next one is pre-index addressing. It means that you have this side, then you just combine the numbers and save into RN first, then you point into the specific locations. And the next one is a post. It means that you use RN as a pointer to the memory first, then after operations you just increase the or decrease the values of RN by using the offset as shown in here. And this is example that I already told you if you can remember. Okay, I go a little bit further. Okay, there are some examples that we have RD with RN in blanket. It means that if every time you find there are some blanket like this, it means that you try to access your memories directly, right? So this one is mean that you use RN as a pointers, point to the locations of memories, and you get the data from that specific address that point by RN and store to RD. For the next one, okay, you have RN and offset. It means that this one is just add RN with the offset and point to specific location in your memories using that address and store into RD and don't alter any value of RN. For the next one, as you can see, you have this mark here, right? Then you can think of you just RN equal to RN plus offset first, then you point to that locations and copy the value and store into RD. This one RN is not changed, but this one RN is changed. Then you can load directly from the labels. And I already told you that for the labels, it means that for the labels you can specific locations, and because of they can specific locations, they can use as the pointers that point to locations inside your memories by using this one. It's very convenient for us because sometimes we don't want to know the location in address numbers in order to get some values, but we can represent that areas or that location using just only labels like this one. When you store in this one is a little bit weird for you because when we would like to store some data inside the address, basically we always say this destination, the first is destinations and followed by the operand, right, or the sort, right? For this one, when you use str as store, the first one become the sort, and the last one it become a vectors that point into the destinations of the memories. Okay, this is just only one case that happens in your assembly language in ARM for the ARM microprocessors. If you do something like this, it's not store from the memory into R, but it means that you store the value inside your R into the memory that point by Rn in this fashions. Okay, and this one you can follow by using explanation in here. Is quite simple, just straightforward. I just mentioned just only this one and this one. They look very similar, right? Just change only LDR to SDR. Okay, and Rn become a pointers, and Rd in this case is a destination, and this one is the sort. Okay, and I would like to explain one more thing about the offset. For the offset, because of this, the offset is immediate, right? And you have the Rn as a pointers that point to the specific location. It means that you need 4 bits in order to store to specific the Rn values. Then for the offset is become immediate, and this immediate just can be can be just only 12 bits. It means that you can have the value offset between minus 4096 to plus 4095. It means that if you have Rn here pointing to here, you can go up 4095 or go down 4095. Okay, somebody will say okay, no problem. Yes, it's no problem at all. And one more thing that maybe you a little bit concerned is mean that if we would like to copy the constant value 32 bit and save into specific registers, we cannot do it, right? Because when we use a move, then we can copy just only 16 bit of immediate and store into the highest or lowest bit of the RD. But if we would like to store all the 32 bits in the registers, we can do a load command instead of move. Then we can put the equal sign here in this one. Then they will copy the immediate values 32 bit and save into RD. Okay, when you use move, let me explain you again. When you use move, you can copy just only 16 bit into RD, and you have MVT and MVN, right? Let's go back a little bit. It's a little bit far. Here's MOVT is mean you use this one, and MOV you use this one. But if you would like to put all the constant inside 32 bit of RD, then you change your command into load, not move anymore. Load RD, comma equal to immediate 32 bit. By using this one, they will copy 32 bit and place into RD directly for use without do anything. Okay, this is examples. If you use LDR load R0 with equal to 0x42, your assemblers, GNU assemblers will change it to move R0 with constant 42s. Because this one is very short, right? You can use this one to store into the R0. But if you put all 32 bits in here, such as a load R0s, comma equal to 0x 2005005, then as you can see, this is 32 bit. Then they can copy all this value and put into R1, just only one line. You don't have to supply into to move. But actually what's gonna happen they actually change your command into load R0 with a PC, comma offset. And what is a PC and comma offset? Actually they will put this constant in specific location inside your memory, and you use PCs and follow by the offset and copy that value and store into R0s. They use the mechanisms of load and store of the memories and to copy 32-bit from memory and place into the R0s, but you don't have to do it by yourself. You just place this constant here and that's it. It will copy the constant this value and put it into R0s. Okay, for the more examples, if we have LDRHH, R3, R5, it means that they try to copy the value inside your memory that point by R5 and place into R3 with the sign half-word. It means 16 bits, but we have a sign will is shown in R3s. How about this one? S3RB, R1, R4, sharp 4. This one will copy the values of R1 because this is store, right? Copy value from the R1 and store into memories that point by R4 plus 4. And you have a B here, it means that you just place it just only 8-bit, not all 32-bit. And you can see here, they don't have any sign after this, and they don't have the post style. It means that R4 is not change the value after this command. Okay, so this one will explain you more. Because of our memories is one address can store just only 8-bit, but our system CPU but our ARM CPU systems, they are 32 bits, right? Therefore, they require 4 address in order to store all the data of the 32 bit. Okay, in this one, if you go something like this offset can be minus 255 or plus 255. Okay, it's okay, can you change this one? Not really. It's 4095 4 minus 2 plus 400 4095. Can you change a little bit? Okay, then we will find out that if we use this command, what's gonna happen if you have R0s, in this case is equal to this number 0x 2000 800s, then you have offset of 4. It means that you combine this number together, you will find out that this pointers will point to address 0x 2008 004, and this one is load. It means that you copy the values in from this address and store into R1. If the information is stored in 0x5b, 0x6a, 0x97, 79, and 0x88, then they will copy this 4 address and store into R1. Okay, right now R1 becomes 0x88, 79, 6a, and 5b. As I already told you, this is a little Indians, right? They use the little to store first. Then when the address is going up, then they can store the more informations of more significant bit in here. Okay, as you can see, they will copy this and put into here. Why I have to show this one? Because sometimes you will you cannot remember that when we try to access our memories, they are jump 4 address at one time, because for the memory they can store just only 8-bit, right? Because we have to find a way to access this one using an alliance. Then they have to make this one just only 8-bit. Then we need 4 address in order to get all the 32-bit data to store into our registers, which is 32-bit registers. Okay, and this one is nothing, they just show a post information that R1 point to the first location, you copy the value into the A, then you just add it by the post prefix, the post addressings, then you will end up with R1 with some value here. And this one just nothing, just you have this expression, right? Then you just add R1 with this value first, and you store this one and point to this one, and you get some information into here. Okay, and this one they belong to the same group is load and store instructions, but this one sometimes you would like to load and store a lot of informations by using just one command, and this one is a command contact that have the contact with the multiple memory locations in the single commands. It means that when you run this one LOD, then you can do RN and register list. Sorry. They try to copy the memory from the memories that are point by register RN and place into the register list in this case. And this one is stored from the register list and this they try to copy the value in register list and place into the memories that point by using register RN. Okay. For the O is options. For the O is option, so what does it mean? It means that if you place O with IA or DB, they will say that they are specific the ways that they will store the address inside your memory in order to store all the information that is in register list in this one. How about these expressions? This expression is option that increase RN every time when you access to your memories. It means that if you have RN and you don't have this side, then after you put everything inside your memories, RN is the same. But if you just make this side appear after RN, it means that they will update RN every time when you put some value inside your memory. Okay, and register list is the register list that you would like to put into your memories. It will come with RA or RA to RC like this. For this one, LDIA, they will say that R4 and R1 to R3s. This one will read the values that point by R4 and they put into R1, R2 and R3 respectively. Okay, and this one they say they read forwards. Okay, because of the R is 32-bit, that's why they need to read forward. How about this one? They would like to store R0 to R7 into the location that point by R9. Then the explanation of this command is they try to store the data from R0 to R6 is 7 words into the location in your memories that point by R9. This is what we do with the multiple memory access, load and store. Okay, let me stop here because right now there is a lot of information you have to take a look and go through again. And we will continue our instruction set in the next slide, in the next video. Okay, it's the end of this video. See you next time.